So we're going to do a new topic today. We're going to talk about evolution. We're going to talk about the connection between evolution and game theory. All right. Now there's going to be an extra I think I already emailed you about this. There's going to be an extra reading on this for the people who want it. There's a reading packet that's available to anybody who wants it. I emailed you all the website where you can order that reading packet and figure out where to pick it up. It's not compulsory. You don't have to look at that reading packet. It's just it might help. In addition, as with last Wednesday, since some of the material here is new, I have written a handout that goes with this lecture, and that handout will appear magically this afternoon on the website. All right, so if things today are fast, don't worry, there's a handout that goes with it. All right, so why look at evolution in the context of game theory? There are really two reasons. The first reason is because of the influence of game theory on biology. All right, it turns out that in the last few decades, there's been an enormous amount of work done in biology, in particular looking at animal behavior and using game theory to analyze that animal behavior. And just to give you a loose idea about how this works, the idea is to relate strategies with genes, or at least the phenotype of those genes, and to relate payoffs to genetic fitness. All right, so the idea is that strategies are related to genes, and the payoffs in the games are related to genetic fitness. And the big idea, of course, is that strategies grow if they do well. All right, so strategies that do well in these games grow, strategies that do less well die out. All right, so we're going to be visiting that today. One thing to bear in mind from the start is there's an important difference between game theory as analyzed in animal behavior and biology and game theory that we've been doing so far in the class, and that is that we're going to think of these behaviors, these strategies played by animals, not as chosen by reasoning individuals, but rather as being hardwired. So if strategies grow, it isn't that some lion or ant has chosen that strategy. It's simply that the ant or lion who has that gene that corresponds to that strategy grows and has many children. All right, so it's important that this is a new idea for us, that these strategies are hardwired. All right, so that's interesting in and of itself, but there's also an important influence the other way. So a second reason for studying this stuff is that there's been an enormous influence from biology, or from evolutionary biology in particular, back on the social sciences. All right. This influence the other way uses evolution largely as a metaphor. And you'll find this if you're a political scientist, if you're a historian, if you're an anthropologist, if you're a sociologist. And let me give you an example from economics, since it's perhaps closer to home. So here's an example. You might imagine some firms in the marketplace. And you could think of these firms not necessarily reasoning out what is the most profitable strategy for them, or what is the most cost-reducing strategy for them. However, so they might just have rules of thumbs to select their strategies. However, in a competitive marketplace, survival of the fittest firms will lead to us ending up with a bunch of firms who have low costs and high profits. All right, that makes sense? So here, competition in the marketplace substitutes for competition in the jungle, as it were. All right, and the analog of a gene dying out is a firm going bankrupt. All right, so this is the kind of ideas we're going to explore. These are the kind of ideas that are going to be in the background for today and Monday. Now, before I go on, I want to put in a couple of kind of important riders. So there are two things that I am not. Right? The first thing I am not is I'm not a biologist. I'm sure there are people in this room who are biologists who know a lot more about the genetic side of this than I do. All right? So I'm not going to attempt to teach you biology here. I'm going to focus on the game theory part. Right? The second thing I'm not is I'm not an American citizen. And I worry slightly when we talk about evolution, because I realize it's very controversial here, and some of you might be from places like, say, Kansas. And if you are from some place like Kansas, then please don't write to your senator about this. All right? Or if they see the movie, just tell them it was some other English guy giving the lecture. All right. So what we're going to actually do is we're going to look at a highly simplified model of evolution, at least for today. All right? We might get onto a more complicated model on Monday, but today it's going to be very highly stylized. So this is going to be our extremely simplified model. And this simplified model is going to do tremendous violence to the biology, but it's really just to fix some ideas, okay? So we're going to focus on what we're going to call within species competition. So the lions are competing against the lions, and the ants are competing against the ants. And the way we're going to think about this is we're going to look at symmetric two-player games. So we look at very simple games. They're only going to involve two players, and they're going to be symmetric games, which means both players have the same strategies, both players have the same payoffs. All right? The way we're going to think of this is we're going to imagine that there's a large population out there, each of whom is playing a particular strategy. And we're going to assume that what happens is we randomly pick two people from that population and pair them up. So everyone in this large population will be randomly paired with someone else. They'll play the strategy that they are hardwired to play, and then we'll see what happens. All right? So the idea here is there's a large population of if you like, animals that are hardwired to play particular strategies, and we're going to have random matching. And the idea here is, when we do lots of these random matching, we're going to keep track of the average payoffs. All right, so what we're going to focus on are the average payoffs of particular strategies when randomly matched in these games. All right? All right? And again, the underlying idea is that relatively successful strategies will grow, and relatively unsuccessful ones will decline. I'm not going to write that. That's obviously the other part of that. So relatively successful strategies are growing, and relatively unsuccessful strategies are declining. All right, now to keep things simple, I'm not going to do any dynamics here. That would take us beyond the math that a lot of you can do in the class. So we're not going to worry about dynamics here, but this is the underlying dynamic. The idea is that if a strategy is successful, that strategy will grow in the population. If a strategy is unsuccessful, it will decline. So this isn't horrible violence to biology yet. It's the next bit that's the horrible violence. All right? So to keep things simple today, we're going to assume that there is no gene redistribution. All right? We're going to assume that there's no gene redistribution. So in principle, what we're looking at is asexual reproduction, which is clearly not a good model, but it will do for today. All right, so you want to think about a practical example of asexual reproduction? Think about root vegetables, or judging from our experiments with the dating game, we better hope that's true for economic majors as well. All right, maybe the fact I'm focusing on asexual reproduction will get me off with the guys in Kansas. Maybe I won't lose my green card after all. All right, so that's going to be our basic story. And the basic idea we're going to use is this. It's an idea due to a guy called Maynard Smith in the 70s, although obviously the big idea goes back earlier. So this is the big idea. Suppose that we imagine that there's a particular game, and there's a large population. So think of yourselves as a large population. And suppose that the entire population were all playing the same strategy, call it S. So they're all hardwired to play the same strategy S. And suppose now that there's a mutation, right? So some small group start playing some other strategy, let's call it S prime. Right? What we want to ask is, will that small mutation group, the S prime strategy, will it thrive or will it die out? If it's true that for all possible mutations, all possible little groups of mutation of people who are playing S prime, they'll die out, then we'll say that the original strategy, the strategy S, is evolutionarily stable. Right? And we're going to write that up more formally later on, but that's just the basic idea. So let's say again, there's a strategy out there that everyone's playing, call it S. We're going to look at a mutation, that's S prime, so a small group of people are going to start playing S prime. They're going to go on being randomly matched, everyone's going to be randomly matched, and we're going to ask if the S prime group does well, in which case they'll grow, or does badly, in which case they'll shrink and eventually die out. If they die out, we'll say that S was evolutionarily stable. That's true for all possible mutations. All right? And just notice when we're randomly matching them, one thing to note is, since there's only a small mutation to start with, most of the time when they're randomly matched, they're going to match against somebody who's still playing S. Occasionally they're going to meet one of the other mutants, but most of the time we're going to have to worry about how the mutants do against the incumbent population. All right, so that was too abstract to really get one's head around, so let's try and do an example. So let's remove our motivation and get down to actually doing some work. All right, so we're going to start with a very simple example that you'll all recognize. Here's a game. It's a 2x2 game, and the payoffs are as follows: 2, 2, 0, 3, 3, 0, and 1, 1. All right, we'll call these strategies cooperate or defect. C for cooperate, D for defect. C for cooperate, D for defect. All right, and you'll all recognize immediately that this game is what? This game is what? This is Prisoner's Dilemma, right? So we're going to start by imagining these animals playing Prisoner's Dilemma. And to put it into context, imagine that these are a group of lions. All right, again, leave aside the fact that it's asexual reproduction for a second. Imagine these are a group of lions, and cooperating means cooperating on the hunt. It means using a lot of energy going after, as you cooperate in a group while hunting. And defecting here would mean not working hard on the hunt, letting the other lions catch the antelope, whatever, and they're just sharing in the spoils. So free riding, basically. All right? Or another example, think about ants with an ant nest, and imagine this ant nest has been attacked by, I don't know what, some other creature. You could imagine that cooperating is joining in defending the nest at the risk of being hurt, and defecting is running away. All right? All right? And we all know in this game roughly how to analyze it. I'm not going to go over that now. I want to ask a different question today. I want to ask, in this model of asexual reproduction, is cooperation evolutionarily stable? Is cooperation evolutionarily stable? All right. Okay. So to try and illustrate that, let's just think about this game being played for real out there. So what we're going to do is, we're going to start off by imagining that you are all, I don't know, ants, lions, what do you want to be? Ants, I think. All right? All right, so you're, from up here, look like ants, right? You're all ants, and all of you have been hardwired to play the strategy C. All right? You've been hardwired to play the strategy C. All right, so life's going on fine, and let's do some random matching here. So suppose, that's going to get me eventually, suppose that we randomly match this ant, all right, so stand up a second, with, right, so this ant gets randomly matched with this ant, all right? All right, so they now play this Prisoner's Dilemma against one another, all right, but both of them have been hardwired to cooperate, right? Both have been hardwired to cooperate, so they both cooperate, is that right? Right, so this ant, whose name is? Lenore. Lenore the ant cooperates, and Wu the ant cooperates. So since they both cooperate, we can look at what their payoff is. Their payoff is cooperate against cooperate, so they get 2. So that's pretty good. So they're doing pretty well in terms of genetic fitness. And suddenly there are 2 ants, right? So this ant produces another ant. Well, it's one without a computer. Okay, so this ant produces another ant. All right, and this ant produces another ant. Sorry, okay, all right. All right, so they're doing fine, right? And the whole population is matching against other cooperative ants, and more ants are being produced, and everything's fine and dandy. All right, everything looks good. All right, sit down a second, sit down a second. All right, now imagine that there's a mutation, a small mutation, and this small mutation involves a group of rather nasty, uncooperative ants. All right, it's a rather scary mutation. So here's our scary mutation. All right, let's use the TAs, right? So the TAs are my scary mutation. So all of the TAs here are the scary mutation. There's another one over there. All right, so there's a bunch. So everyone else is still playing cooperate. There's this vast number of cooperative ants, but now there's this small number of ants with this mutation that says don't cooperate, play D. All right, so let's see what happens with random matching. So a lot of these cooperative ants are still matching with each other and doing fine. But that's not the point. What we're worried about is what's going to happen to the mutants. All right, so let's pick our representative nasty mutants. So that's going to be Rahul, all right? All right, so Rahul is our scary mutant. All right, and let's go back and randomly match him against one of our incumbent ants, our nice cooperative ants. Let's pick this one, all right? So it just happens he's randomly matched with this cooperative ant. And this cooperative ant, whose name is Nick, is hardwired, since he's a regular ant, he's hardwired to play cooperate. So he's going to play cooperate. Say cooperate. All right, I should put the mic, but never mind. And meanwhile, do we have a mic handy? Thank you. All right, so he says cooperate, but unfortunately, he's been matched against the nasty, uncooperative ant. It's not that he's nasty, he's just been hardwired to say
not cooperate.
Not cooperate, to say defect. All right, so what's going to happen now? All right, so unfortunately for Nick, he, the cooperative ant, was matched against a not very nice ant. He was playing C, and Rahul was playing D, so Nick's payoff is 0. So we went from 1 Nick to being no Nick, right? He got wiped out. All right, and Rahul, meanwhile, he got a payoff of what? What was Rahul's payoff? Rahul's payoff 3, so suddenly there's not just Rahul, but there's the mutation is growing. All right, and now we go on matching each period. Some of you are going to be matched against other cooperative ants, and you're going to be doing fine. But every now and then, and actually increasingly often, you're going to be matched against one of our mutants, and those mutants are going to grow. Those mutants are going to go on growing. Now, it's true that every now and then a mutant's going to meet another mutant. Is that right? Right? But we don't have to worry about that. All we have to worry about is, are they going to die out early on? It's going to be very rare for them to meet another mutant, at least early on. All right? So the strategy cooperate is evolutionarily stable if this small mutation, there's our small mutation, disappears and doesn't turn into a bigger mutation. All right? And of course, in this case, as we just saw, the mutation didn't die out, it actually grew. All right? So be formal about this and be careful. For the strategy to cooperate to be evolutionarily stable, it needs to be the case that the mutation actually dies out on average. And here, far from dying out, it grew. We now have lots of these nasty TAs. All right, people understand? All right, so let's just, thanks. All right, so let's just try and do that a little bit more formally on the board. All right, that was the basic idea, or the basic graphics of the idea. But let's look at it a little bit more formally. So we basically have cooperative ants and a few mutant defector ants out there, so mutant not cooperative ants. And what we want to keep track of are their average payoffs in random matches. All right? So the incumbent ants, the cooperative ants, they're playing, we're interested in their payoff, and they're playing a population that's mixed. Almost everybody in the population is cooperative. So let's say 1 minus epsilon of the people they're playing against, where epsilon is a small number, very small number, are also cooperative. But every now and then, like our poor friend Nick, every now and then they're going to come across a nasty mutant. They're going to come across Rahul. All right? So what's their payoff going to be on average, their average payoff? Okay, so 1 minus epsilon of the time. We can actually think of this mix here, so it's 1 minus epsilon and epsilon. 1 minus epsilon of the time, they're going to meet another cooperative ant and get a payoff of 2, all right? But epsilon of the time, they're going to meet Rahul and get a payoff of 0. Is that correct? So that's their average payoff. Now how about the mutants' payoffs? So the mutants, there aren't many of them around, but they are also playing against the same mixed population. 1 minus epsilon of the time, they're going to be matched against a cooperative ant, and epsilon of the time, the two mutants, the two TAs, are going to play off against each other. All right? Let's have a look at what their payoff is. So their payoff is 1 minus epsilon. They get a payoff of 3. That's what we saw when Rahul met Nick. And the other epsilon of the time, Rahul meets Jake or somebody and has to make do with a payoff of 1. All right? But if we keep track of this, what do we have? This equals 2, 1 minus epsilon, and this equals 3, 1 minus epsilon plus epsilon. Is that right? All right, and clearly, I hope this is clear, the payoff to the mutant is bigger. Everyone happy with that? The payoff to the mutant is bigger? Which means the mutation is not going to die out. In fact, it's going to grow. Mutation is not going to die out. So we can conclude that C is not evolutionarily stable. I'm going to start using ES for evolutionarily stable. All right? All right, so in this particular game, evolution is not evolutionarily stable. So we might ask, what is evolutionarily stable in this game? Well, it's not going to be hard to figure it out, but since there's only one choice, I claim that D is going to be evolutionarily stable. But let's just prove it. So is it going to be the case that these mutants will eventually take over the whole population and everyone will end up looking like a TA and being uncooperative? All right, so they're busily asexually reproducing all the time, they get bigger and bigger, and is it in fact the case that once they've conquered everything, that they're evolutionarily stable? So is defect evolutionarily stable in this game? All right, to figure that out, we have to do exactly the reverse experiment. So the experiment now is, imagine everyone in the population, all of you guys, all of the students in the room, are nasty, non-cooperative, defecting ants. All right? All right? And you're going along, and most of the time you're meeting each other all the time for now, and you're getting a payoff of 1. And now there's a mutation, but this time the mutation isn't the scary non-cooperative mutation that we saw before with Rahul. It's going to be Murtu over there, all right? And Murtu is a nice mutation who cooperates. All right, so Murtu is our nice cooperative mutation. All right, let me just get the camera to pan on poor little Murtu. All right, so there's poor little Murtu, who's the only little cooperative mutation in the room. Wave. All right, there we go. Okay. All right. All right. And what's going to happen to our cooperative mutation? All right, so most of the time, you non-cooperative people are matching up against each other. We can figure out what your payoff is. So the uncooperative incumbents, they're playing a population that is 1 minus epsilon non-cooperative, and epsilon of the time, they meet Murtu. All right, so what's their average payoff? So let's be careful. Let's switch things around up here, just to make sure we can see what happens. So switching things around on our chart up here, we're now looking at the case where there's 1 minus epsilon non-cooperators and epsilon cooperators. All right, so these you guys, you non-cooperative ants, are most of the time meeting each other, and when you meet each other, you're getting a payoff of 1. So 1 minus epsilon of the time, you're getting a payoff of 1, but epsilon of the time, you're doing great, because you're meeting Murtu, and unfortunately you're beating up on Murtu. All right, and how's she doing? Well, she's a cooperator, and 1 minus epsilon of the time, she's meeting you guys, and epsilon of the time, she meets another nice cooperative ant like Jake. All right? So her payoff is 1 minus epsilon of the time, she gets nothing, and epsilon of the time, she does pretty well and gets 2. But it's only epsilon of the time. Is that right? So far, so good. So what's going to happen to this mutation? Well, the incumbent population, their average payoff comes down to being 1 minus epsilon plus 3 epsilon. And Murtaugh's payoff, the mutant, ends up being 2 epsilon. All right? So unfortunately, these nasty ants are thriving, and Murtaugh gets wiped out, so you can sit down again. All right? So what have we shown here? We've shown that defect, not cooperate, is evolutionarily stable in this game. Right? Any mutation, there is only one possible mutation, any mutation gets wiped out. All right? Think about these two different models here. The first, not different models, but different metaphors. So we started out with this population of relatively nice people, and we had a nasty mutation. So think of the movie Alien. Actually, don't, because it's a horrible movie, but all right. All right? And if you remember that horrible movie, Alien or Species, think of the movie Species, an even worse movie. Right? Think of the movie Species. That was Rahul, and he grew, albeit asexually, very rapidly. That's a pretty scary movie, right? Right? Conversely, when we had this population of nasty people, and we tried to have a nice little invasion of a nice mutant, so think of the movie E.T., unfortunately, E.T. got squished. All right? All right? So that's the two extremes. All right. So what is a lesson that we can actually draw from this? All right. So there's a lesson here. And the lesson, I guess there's going to be two lessons here, but let's start with one. The first lesson here is that, well, let's just put it on the board first of all. Nature, the outcome of evolution, nature, can suck. All right? So again, we could use a more formal term, but this is an important lesson. There's a tendency for some people to think that if something arises as a consequence of evolution, if something is natural, if something is in nature, it must therefore be good in some moral or other way, efficient or something. All right? And what we're seeing here is in this game, the consequence of nature is a horrible consequence. All right? For those people who doubt that nature can be pretty unpleasant, have a look at yesterday's science page of the New York Times and read the piece about how baboons basically kill baby baboons. The biggest cause of death among baby baboons is infanticide. Right? This is evolutionarily stable, it turns out, and they explain why in the Times. It isn't pleasant. All right? So nature can suck. Nature can be pretty inefficient. Okay? Now, this raises a question in this particular game, because look at the examples we started with. We started with lions who were thinking about, or not thinking about, they weren't thinking about, they were hardwired to go after antelope and either cooperate or not. And we thought about ants who were hardwired to defend the nest or not. And we all know from watching endless nature shows as children on TV that actually lions do cooperate when they go after antelope, and actually ants do defend the nest when it's invaded by a spider or something. Is that right? Looking for some nodding, is that right? Yeah, okay, good. So what happened? What's wrong with our model here? We've argued here that in this model, nature's going to produce this non-cooperative behavior. We know there are examples of cooperation in nature. What's going on? What are we missing? Yeah, can I get a mic in it's here. Let me do it. I'll do it. Yeah, so what's going on?
Different communities might compete against each other, so one community that doesn't have any of these mutations and stays cooperative might succeed, so communities in general don't have as many mutations.
Okay, so that's an interesting idea. So part of this is because we're focusing on within species competition rather than the cross-species competition. That turns out to be a complicated idea, and large literature on it, and it's actually a little difficult. I was looking for, but it's good. It's a good suggestion. I was looking for something simpler, actually. Let me come back here. So yeah.
Do these species have ways to detect cheaters and punish them?
Okay, that might be a possibility, and that certainly there is some evidence of that, but not much. Again, we're looking at pretty high primates by the time you get to that. Something simpler, something you should all have on your mind all the time if you're normal teenagers.
The payoffs could change as the proportion of cheaters increases, so you're not going to get the payoff of 3 if everyone's cheating.
All right, but it's true that you're going to get a different expected payoff, but that isn't the payoff they get. I'm thinking of something really simple that, let me repeat, I'm guessing is on all of your minds as teenagers. Let's see if that hint's going to get the right answer. Yeah.
Ants are not asexual.
Right, right. The assumption that's really driving this here is the assumption of asexual reproduction. Right? Sexual reproduction with gene exchange is going to make a difference. Why? I don't want to delve too much into the biology here, but the main why is what matters is survival of the gene, not survival of the individual ant or individual lion. So if you have sexual reproduction, you get gene redistribution among children and cousins to a less extent. All right? So provided the other ants in the nest are closely enough genetically related to you, and provided the lions are close enough related to you, then it may turn out to be that you will cooperate, and that in fact does change the payoffs of the game. It doesn't change the payoffs for the individual lion or ant, it changes the payoffs for the gene. All right? Now, if we have time, we'll come back and look at that on Monday. And even if we don't have time, in the reading I've left for you in the reading packet, it goes into that in some detail. All right? It's a much more complicated model, but that's where we're going to get, for the most part, that's where we're going to get cooperation from, rather than from the other points that you made. All right? So sex can make a difference here. But we're going to stick with asexual reproduction because it's easier to analyze, and stick with it for the minute. And what we've learned, the second lesson we've learned here, I'm going to generalize from this lesson. We learned that a strategy that was strictly dominated was not evolutionarily stable. Right? All right? So I've only shown an example here, but we'll extend from the example. All right? So if a strategy is strictly dominated, and of course cooperate is strictly dominated here, then it is not evolutionarily stable, at least in this simple game of just asexual reproduction. And even though I haven't proved this here, the idea is exactly the idea of this example. So let's just try and talk it through. Suppose a strategy was strictly dominated. How do we know, how can we see that it will not be evolutionarily stable? Somebody? Where are my pre-med majors? I mean, not pre-med majors, but my pre-med people. Now, they're all hiding now. I know you're out there because I've seen your forms, but never mind. Okay, so why is this dominated strategy not evolutionarily stable? I want to try this out. Yes? Yeah.
The strategy that dominates will be a successful mutation.
Good, good. So the strategy that dominates, the strategy that does the domination of this strictly dominated strategy would be a successful mutation. If it enters, it does well, not just against this strategy, but against any mix involving itself and this strategy. All right, so the strictly dominator strategy will invade. All right, so we can't have strictly dominated strategies surviving in evolution. All right. Let's do another example, and we'll see if we can learn some more. So this is going to be a slightly more complicated example. Let's have a 3x3 game. So here's our 3x3 game, and we'll just label the strategies A, B, C, and A, B, C. And once again, we're going to focus on symmetric games, so this game will be symmetric. 2, 2, 0, 0, 0, 0, 0, 0. Lots of zeros in this. 0, 0, 0, 0. 1, 1, 0, 0, 1, 1, 0, 0. All right, this is a symmetric game. Okay, and if we look at this game a little bit, I don't want to look at all of it. I want to ask the question, is strategy C evolutionarily stable? And strategy C evolutionarily stable. Let's go back to our experiment. What does it involve? Imagine everyone in the room is hardwired to play C. Could that population be invaded by a mutation? All right. So what do we think? What do we think? Is C evolutionarily stable? Who thinks it is stable? Who thinks it's not stable? Right, so most of you think it's not stable, so you must have some idea why. Why do we think it's not stable? Let me just try and cold call a little bit. Anybody? Let me sample somebody. If it's not stable, it must be it's going to get invaded. So who's going to invade it? Can we try this gentleman? Have a guess who's going to invade it?
Strategy B.
Strategy B. Okay, that's correct. Okay, so your name is?
Greg.
So Greg is saying strategy B might invade here. Let's have a look. Let's see what happens. All right? So suppose there's an invasion of B. So again, the TAs are playing B, everyone else is playing C. And let's see how these incumbent genes do. So C is playing against 1 minus epsilon of the population who are playing C and epsilon who are playing B. And its average payoff, well, 1 minus epsilon of the time, it'll be matched against essentially itself and get a payoff of 0. All right? But epsilon of the time, it will be matched against a B and get a payoff of 1. All right, everyone agree with that? Right, so 1 minus epsilon of the time it meets itself and gets nothing. Epsilon of the time it gets lucky and it meets a TA and gets a payoff of 1. How about those B invaders, the TAs in the class? So 1 minus epsilon of the time, they're going to meet C's, and epsilon of the time they're going to meet B's. And 1 minus epsilon of the time, therefore, the B is meeting a C and getting a payoff of 1. Right, so 1 minus epsilon of the time, the TA is meeting one of you. And epsilon of the time, the TA is meeting another TA, playing B against B, and getting 0. All right, so this works out as epsilon, and this works out as 1 minus epsilon. All right, but notice that if epsilon is small, if there are just a small number of these mutations, 1 minus epsilon is bigger than epsilon. Is that right? And that means that this mutation will not die out. Right? It'll probably go on, we can actually say a bit more, it'll probably go on growing until it's roughly half the population. All right? But in particular, it won't die out. Since it won't die out, since the mutation doesn't die out, we can conclude that C is not evolutionarily stable. All right, everyone okay with that? Everyone okay with that idea? Now this example is a little bit more complicated than the previous example because it turns out that the invading mutant population, the population B, is itself not evolutionarily stable. Right, everyone see that? Right, C wasn't evolutionarily stable because it got invaded by B. Who's going to invade B? Who's going to invade B? C is going to invade B. Turns out everything's exactly symmetric here. So even though we're arguing that C is not evolutionarily stable because it's invaded by B, it doesn't have to be the case that the successful mutant is itself evolutionarily stable. Right? So in this particular example, the invader, namely B, is itself not evolutionarily stable. Nevertheless, it doesn't die out when it invades a population of Cs. All right? But there's a second observation I want to draw off this one. I'll give us some better chalk here. I'm not finding it. All right. There's a second observation I want to draw off here. What do we observe? What else is true about this, about both C and B? So what's true about everyone playing C or everyone playing B? What else? Just going back to what we've learned in the course so far, what do we think about everyone playing C? So if everyone's playing C, we'd be looking at an object like this, C comma C, right? And we might ask the question, is C comma C what? Is it a Nash equilibrium? All right, so is CC a Nash equilibrium? Here we asked, was it evolutionarily stable? We found it wasn't. Now let's ask a different question. And forget evolution for a second. Is CC a Nash equilibrium? Well, that's a question you all should be able to answer for the midterm. So somebody tell me the answer. It's not a Nash equilibrium. How do we know it's not a Nash equilibrium? What do we have to do to show it's not a Nash equilibrium? We have to show that there's a profitable deviation, right? Right? So shout it out, what's the profitable deviation here? The profitable deviation is B, right? It's not, no, because B is a strictly profitable deviation. Right? Right? B is a strictly profitable deviation. Notice that the thing that was a strictly profitable deviation was the same thing that would have invaded the population of C's in the context of our ant's nest, in the context of this classroom being an ant's nest and looking at evolution. Is that right? Right? So what have we just learned here? Well, this idea turns out to be general. The idea is, if a strategy S, right, perhaps I should make this a lesson. If a strategy S is not Nash, so in other words, SS is not a Nash equilibrium, it's not a Nash equilibrium, then S is not evolutionarily stable. All right. If S is not Nash, then S is not evolutionarily stable. All right? A little bit of logic, we can flip that around, and we'll say what that actually tells us is, it's equivalent to saying, if S is evolutionarily stable, then SS is a Nash equilibrium. That's the equivalent way of saying that. All right, so what's the idea here? Let's look at the first line rather than the second line. It's pretty easy to understand. The idea here is if a strategy is not Nash, what that means is there's some other strategy that would be a strictly profitable deviation. And that's enough to tell us that S cannot be evolutionarily stable. Why? Because take that same strategy that was a strictly profitable deviation, B in this case, and that strategy can be thought of as the mutation that's going to invade the strategy we started from. Right, everyone see that? Say it once more. Suppose a strategy SS is not a Nash equilibrium. Right, that means there's some other strategy, S prime, say, that is a strictly profitable deviation. Now think of that strictly profitable deviation, S prime, as a mutant invasion. So now Rahul is hardwired to play S prime. Right? Since it was strictly profitable, it's going to be was it strictly profitable as a deviation, it's going to be successful as an invader. All right, so again, I haven't formally proved it, but that's exactly how the proof would run. All right, so let's pause for a second and just see where we are. All right, what we've managed to show is there's a connection here between dominance and evolutionary stable. We've said if a strategy is not dominated, it cannot be evolutionary stable. And we've also begun to show a connection between Nash equilibrium and evolutionary stability. So two of the ideas we've developed over the last 6 weeks are re-emerging in this completely other context of animal behavior. The idea of dominance and the idea of Nash. And so far, how far have we got? We've said that if something's going to be evolutionarily stable, it better be the case that it's also Nash. All right? And that raises, I think, a natural question, which is the opposite true? It would be really pretty great if it were true the other way around. If I could show that if a strategy was Nash, then it would necessarily also be evolutionarily stable. And that would be pretty cool, right? So this idea we've spent a lot of time developing in the class turns out to be the key idea. Unfortunately, life isn't quite so neat. Let's see why. All right, so what I'm going to do is I'm going to show you an example, and what this example is going to illustrate is that we can find Nash strategies that are not evolutionarily stable. And the example is embarrassingly simple. Here's a game. It's a two-player, two-strategy game, and the payoffs are 1-1, 0-0, 0-0, 0-0. All right, this is kind of an embarrassingly simple game. All right, what are the Nash equilibria in this game? Well, let's go through slowly. All right, if player row is playing A, then column's best response is to pick A. And if row is playing B, then column's best response is either to play A or B. Right? If column is playing A, then row's best response is to choose A. If column is playing B, then row's best response is either A or B. All right, this is kind of exercise that is almost second nature for you guys now. All right, so we can conclude by looking where these best responses coincide that the Nash equilibria here are AA and BB. Okay? Everyone happy with that? Should we be looking like this is, yeah, this is easy, right? All right. So, all right. But let's look at this second Nash equilibrium, the BB Nash equilibrium, the one that's down here. Right? Is B evolutionarily stable? Is B evolutionarily stable? Well, again, let's think about it. Let's just think through the exercise. Suppose the entire class were playing B. All right? Wake up the guy in the middle and tell him he's playing B too. Him, yeah, okay? All right? The whole class is playing B, all right? And suppose there's an invasion. What could the invasion be? The invasion better be an invasion of A's. All right? What's going to be the expected payoff, or the average payoff, of the incumbents, of all of you in the class who are playing B? Well, without doing it too laboriously, 1 minus epsilon of the time you're going to meet another student, in which case your payoff, in which case you'll be playing B against B and your payoff will be 0. And epsilon of the time you're going to meet a TA, and these TAs are playing A, but again, you'll get 0. So your average payoff will be what? 0. All right? Payoff will be 0. All right? So if you're incumbent and you against this mix, your payoff will be 0. And if you're an invader, so how's Rahul doing this time? Rahul's playing A. 1 minus epsilon of the time, this A is playing against a B, right? So 1 minus epsilon of the time is playing against a B, right? So 1 minus epsilon of the time, Rahul meets a student and gets a payoff of 0. But epsilon of the time, Rahul hits it lucky, and Rahul meets another TA. Rahul meets Jake. And when he meets Jake, his payoff is 1. Is that correct? Is that correct? So his total average payoff is epsilon, which is bigger than 0. All right? So indeed, it turns out that Rahul's gene is going to grow, the B's are going to shrink. BB was Nash, but it's not evolutionarily stable. It can be invaded. All right? Everyone see that? Everyone see how that invasion works? So the key to that invasion was when Rahul met another incumbent student, he did no better than the students did against students. But on those rare occasions when Rahul met another TA, he made hay. Or not hay, it's asexual reproduction. He got a payoff of 1. All right? And those rare occasions were enough to make Rahul grow and thrive, whereas the B's, relatively speaking, shrink. All right, everyone happy with that? Yeah? Okay, so what we have here is an example of something that is Nash, but is not evolutionarily stable. Can anyone say, what's special about this example? How did I rig this example? There's something really kind of knife edge and rigged about this example. What's rigged about this example? Anybody? Don't want a cold call on this. No takers? Everyone's kind of in that pre-midterm scared mode. Yeah? Yeah, try, yeah. This guy's rescuing, this guy is saving the class today. Someone else has to get in. Okay. What's your name again?
Stephen.
So Stephen is saving the rest of you, but go ahead, Stephen.
B is only a weak best response to anything.
Good. So what's true about this example is that although B is a best response against B, it only is so weakly. Is that right? It's only so weakly. Right? If, in fact, we got rid of Nash equilibria that relied only on weak best responses, then we wouldn't be able to produce this example. Right? So in particular, if we looked at Nash equilibria where the Nash strategies was strictly a best response, it was strictly better than playing any other pure strategy, those cases would be evolutionarily stable. Right? Anyone remember what we call Nash equilibria where the Nash strategy is a strict best response? We call them strict Nash. All right? So what is in fact true is that if S is a strict Nash, a strict Nash equilibrium, by which I mean S is a strict best response to S, then S is a Nash equilibrium. Sorry, and S is evolutionarily stable. All right. Excuse me. Okay, so we've been only semi-formal so far. I haven't really put up a formal definition, and what I've been groping towards slowly is a connection between an idea growing out of biology, namely evolutionary stability, and an idea growing out of economics and mathematics, namely Nash equilibrium. And what I want to do now is I want to show you formally how are these connected. I'm not going to prove this part of the class because a proof is a bit lengthy, but I will include a proof on the handout that's going to be available this afternoon. I'm just going to argue it for now. There we go, there's some chalk. All right? So what I want to do first is I want to write down a formal definition of evolutionary stability. And it's a definition that comes out of biology, and it's a little bit of a, you're going to see, it's a little bit of a mouthful, this definition. All right? So for those people who are kind of a little bit sleepy, you need to wake up a little bit, because this is going to be a little bit of a difficult definition. All right? But this is the definition that came out of biology. This is a formal definition. It comes out of biology, and in particular, it's due to a guy called Maynard Smith, who wrote this in 1972. So obviously the earlier idea is due to Darwin, but this formal idea is due to Maynard Smith. All right, so here's our formal definition. So in a symmetric two-player game, so everything we've been looking at so far, the pure strategy S, let's call it S hat to give it a name, S hat, is evolutionarily stable, and again I'll just use ES for that, but let me be a little bit nerdy here. I'm going to say in pure strategies. It's evolutionarily stable in pure strategies. I'm putting this in because we're going to come back on Monday and consider mixed strategies. Right? So it's evolutionarily stable in pure strategies if, and just leave a little bit of a space here, because I'm going to need a little bit of space between these next two lines. Leave a little space here. All right, so here's our big mouthful. What we need is 1 minus epsilon of the payoff of playing S hat against S hat, plus epsilon of the payoff of playing S hat against S prime, has to be strictly bigger than 1 minus epsilon of the payoff of playing S prime against S hat, plus epsilon of the payoff of playing S prime against itself. All right? This has to be true for all possible deviations S prime. But we also, this is why I need the extra line, and for all mutation sizes epsilon less than some epsilon bar. All right, now, this is why I need to go back and just be a bit more careful. So I'm going to write on this extra line, there exists an epsilon bar. All right, that's why I left that extra line there. So this looks like very nerdy things. Let's talk our way through it. All right, what's it saying? It's saying that S hat is evolutionarily stable if, against all possible mutations, so all possible versions of Rahul, S prime, all right, the payoff of S hat against the subsequently mixed population is bigger than the payoff of S prime against the subsequently mixed population. Let's see why that's so. So this on the left is the payoff of S hat against a population in which 1 minus epsilon of the population, like it, is playing S hat, and epsilon of the population is like Rahul. right? Because 1 minus epsilon of the time it meets something like itself, and epsilon of the time it meets a TA. All right? Conversely, on the right-hand side, we have the payoff to the mutation. The payoff to the mutation is 1 minus epsilon of the time the TA meets a student and gets the payoff of S prime against S hat. Epsilon of the time the TA meets itself and gets a payoff of S prime against S prime. And we have this inequality we had before that says the mutation, the invader, has to do worse, so it dies out. All right? So the nasty bit of this definition, the part that's a little bit, if it takes a while to get your head around, is this qualifier about the size of mutations. And all it's saying, I mean, ignore the math of it, all it's saying is this better be true for all small mutations. All right? You could think of that as saying this has to be true for all small mutations. So this definition from biology is it exactly mimics the argument we went through several times now, both using the class and using the board and figuring out average payoffs. All right? This is an ugly definition. Everyone agree this is kind of ugly? All right? So now what I'm going to do is I'm going to give you an entirely different definition. It's also going to be ugly, but a little bit less ugly. All right, so think of that as definition 1, and it came from biology. It came from this paper in 1972. I think it was in Nature by Maynard Smith and co-authors. And think of this other definition that's coming out of economics. So definition 2. A strategy, S hat, oh, I should have the same qualifier, in a symmetric two-player game. Okay, same thing to start off with. A strategy S hat is ES in pure strategies, so same as we had before, if two things. Thing number 1, let's call it A, if S hat is a Nash equilibrium, is a symmetric, obviously, is a symmetric Nash equilibrium of the game. We're not done yet. Let me just write down what it means to be a symmetric Nash equilibrium of the game. What does that mean? That means, i.e., the payoff of S hat against S hat must be at least as big as the payoff of S prime against S hat for all S prime. Right? That's a standard thing we've seen many, many times. It says S hat is a best response against S hat. All right? Not quite done yet. And B, what else do we need? We need if this weak inequality I wrote above is actually an equality, if the payoff of S hat against itself is actually equal to the payoff of S prime against S hat, then the payoff of S hat against S prime must be bigger than the payoff of S prime against itself. Right? This is still a bit of a mouthful, but I claim it's going to end up being a little simpler to think about. Right? So what it says again, it says S hat is evolutionarily stable if it's a Nash equilibrium. Right? That's basically this. And if it's only a weak Nash equilibrium, if there's a tie, then it better beat up on the mutant. Right? And it better beat up on the mutant when it meets the mutant. All right? So I'm going to try and give you an intuition as to why this is true in a minute. But first, I want to tell you why you should care about this. So without getting too religious, I want to tell you why I think this is an exciting result. Why am I dragging you through more algebra than usual? So I think there are two reasons why this is an important result. The first is it's going to turn out that when we analyze games, it's very easy to check definition 2. Right? it's going to turn out it's very easy to check definition 2. It's really rather a pain to check definition 1. Why? Because you've got to keep track of these epsilons and so on. But the fact that definition 2 is equivalent to definition... Did I say that? That's the point. The fact that definition 1 and 2 are equivalent, so 1 is equivalent to 2, the fact that these definitions are equivalent means we only have to check the second definition. And that's easy. So when biologists are setting up experiments involving wasps or ants or lions or chimpanzees, provided they can check this in the game, they're done. And that turns out to be easy. And we'll see that on Monday. All right, that's the sort of instrumental reason. All right, now I want to give you the religious reason why you should care about this. All right, so let me just try and... I often find that this appeals to like a third of the students, and the other 2/3 of the students think I'm completely bonkers at this point. Okay, so that's fine. You can think I'm bonkers, I'm fine. I want to guess, for the third of you who are nerdy like me, I want you to sort of see the appeal of this. Here we have two ideas. One idea arises out of biology. I say it arose from Maynard Smith, but it really comes from Darwin. So it's a 19th century idea in biology. It's probably the most important idea in biology in the 19th century. It may be the most important idea in biology for 200 years. Is that a fair judgment? Right? The notion of evolutionary stability. Right? The other idea comes out of economics. It's looking at Nash equilibria and strict Nash equilibria and so on. Right? Up there we've got biology. Down here we have economics. This is an idea that emerged in economics in the 20th century, in the 1950s. Right? So roughly 80 years after Darwin. Right? This is a big idea in economics. This is a big idea in biology. So what appeals to me, because I'm kind of a nerdy kind of guy, is I think it's kind of wonderful that those two ideas are almost the same. Right? I think it's kind of, it's a beautiful thing that those two ideas are kind of the same thing. And now you are looking at me and think I'm bonkers, okay? So let me push it harder, all right? So think about the great intellectual coincidences of earlier periods. Think about the 17th century. In the 17th century, people figured out that the mechanical laws that governed the rotation of the planets were at least approximately the same as those that governed a clock. Right? The basic laws of Newtonian physics were the same. And they thought this was a wonderful thing. Right? They had these completely different areas of intellectual pursuit, and they turned out to be the same. The scientific revolution said they were the same. Right? And for those people who chose to continue believing in God at that point, they thought of God now as being what? As being a heavenly clockmaker. Right? It was a wonderful moment. So here, in our own time, or perhaps just before it, we see a similar thing, right? Here we see, one of the most important ideas in science coinciding with one of the most important ideas in economics, right? And where does this lead us? Well, now, I guess, I mean, the bad news is this may make a lot of people doubt the existence of God, I guess. That's going to get me in trouble. I didn't say that. But at least if you did go on believing in God, you're going to have to believe God's an economist. That's a pretty good thing. All right? All right? So that's my little religious piece on this. All right, now I want to spend the last 10 minutes, having told you this wonderful thing, trying to convince you that it's true. And again, there's a proof on the handout that you can read on the web. I just want to give you an idea of why it's true. Okay, so here we go. I need some space. Well, okay. All right, so what I want to convince you of is that this definition, this kind of game theory definition, this econ definition, implies the one above. The one above we've kind of already argued several times today corresponds to the notion of evolutionary stability. We talked about it several times. We wrote down these kind of equations several times. So I want to convince you that this one implies that one. All right? Okay. So what do I have to convince you? So let's imagine, let's fix... Okay. There's no way of getting you to see that one without... No, never mind. That was a bad idea. Never mind. Okay. Let's bring it back in. The embarrassment of playing with heavy boards here. All right, let's try and shoot this one up. If you ever think of asking your dean about some new technology for Yale, we might think about having some slightly lighter blackboards, just for the evolutionary stability of the average weakling economist. All right. All right, so what we're going to do is, let's fix a strategy S, hat, and suppose S hat is in fact Nash. All right, so that's what I want to convince you of, is that S hat is going to be evolutionarily stable. So I claim there's two possibilities. There are two cases. Right? The two cases are, either it's the case that S hat against S hat does strictly better than S hat against S prime for all S prime. Right? So let's be careful. Since we know it's Nash, we already know that the payoff of S hat against itself is at least weakly better than any possible deviation. That's what it means to be Nash. Right? So everyone agree with that? We know that S hat is the best response to S hat, so it must be weakly better than any possible deviation. All right, so let's take the first case where actually it's strictly better. And let's go back to our classroom example and suppose that let's go back to the first definition by going back to our metaphor of the class. So you guys are all ants, all right? And suppose that every student in the class is playing S hat. Right? You're all playing S hat. And suppose it's the case that, in fact, the payoff of S hat against S hat is bigger than the payoff of S hat against S prime. And suppose that a mutation arises. Sorry, Rahul, here we go again. Suppose a mutation arises. Here's Rahul, our mutation. Right? And he's going to be randomly matched against one of you guys. Right? So let's compare Rahul's payoff against this gentleman's payoff. Stand up a second. Your name is? Pat. All right. So Pat is our typical S hat incumbent ant. Doesn't look like an ant, but never mind. You know, stretch your imagination a bit. And most of the time, what's happening? Most of the time is Pat is being matched against one of the rest of you. And when he's matched against one of the rest of you, he's getting the payoff of S hat against S hat, which is US hat, S hat. All right. That's what he's getting most of the time. Right. And every now and then, he's meeting a mutant. Okay, fine. Okay, fine. So every now and then he's getting a slightly different payoff. But most of the time, he's getting a payoff which is US hat, S hat. All right? What about Rahul? So Rahul, okay, every now and then, he's going to be lucky and meet another TA. But most of the time, almost all the time, he's being matched against one of you. For example, he's matched against Pat. Right? And when he's matched against Pat, his payoff is US hat, S prime, which is lower. Right? So Pat's payoff almost all the time is US hat, S hat. And Rahul's payoff almost all the time is US hat, S prime. But our assumption is US hat, S prime is lower, so Rahul's going to die out. Okay? Okay, so in this case, Rahul dies out because most of the time he's playing an incumbent and just doing horribly. Okay, sorry, Rahul. Okay. Okay, everyone convinced by that? So in this case, the mutant dies out. So the mutant dies out because she or he meets S hat often. Right? The mutant meets the incumbent often and just does horribly against the incumbent. That's the first way. That's the first case. That's case one. And case two is, it could be the case that, in fact, Rahul does pretty well against the incumbents. Rahul does pretty well against the incumbents. But unfortunately, for Rahul, could be the case, but in that case, according to definition B, Rahul doesn't do so well against other TAs. All right, so this is case two. Case one was Rahul that gets beaten up whenever he meets one of you. Sorry, Rahul, getting beaten up a lot here, but Rahul gets beaten up when he meets one of you. And here's the case where Rahul is doing fine against you, but he does horribly against incumbents. So that's the harder case. Let's talk through that case. So back up again. So Rahul, sorry, again, you're up again. All right, so once again, you guys are all playing S hat. There's a mutation of Rahul's playing S prime. All right, and let's get Pat up again. All right, so when Pat meets one of you guys, so let's pick out one of you guys. So let me pick up, your name is? Christine. So when Pat meets Christine, which is most of the time, he does okay. And when Rahul meets Christine, which happens most of the time, he does exactly the same. So if you just compared them in their random matches against Christine or the rest of you, they're the same. All right? But every now and then, thanks Christine, every now and then, instead of every epsilon of the time, rarely, Rahul is going to meet Jake. Oh no, Jake's writing. He's going to meet Kai. All right? All right, second. All right? And on those occasions, let's see what happens. So when Pat meets Kai, he does pretty well. And he gets some big bonanza. He gets a much bigger payoff than when Rahul meets Kai. They just do horribly against each other. All right? And the fact that they do horribly against each other causes them to die out. All right? All right, so let's talk this through. There were two ways in which Rahul could die out. One is he dies out because he does horribly against you. And the second way he can die out is if he does equally well against you as you do against yourself, but he does horribly when he meets the other TAs. Right? In either case, you guys are evolutionarily stable and Rahul's in trouble. All right? Was that convincing enough an argument? There's a formal proof. Thanks, guys. There's a formal proof in the handout, but this will be enough to get us started. All right? So in this case, the mutant does okay against S, against S hat, but gets clobbered, or does badly, let's say, against S prime. Right? Right? So mutants that are going to die out are those that do badly against incumbents or do badly against themselves. In either case, S hat will be evolutionarily stable. All right? Now, next time, I want to take this further in two directions. I want to see what happens about evolutionary stability in more complicated games, for example, in cooperation games. And we're going to see that evolution doesn't do great in cooperation games. Right? And we're also, if we have time, going to look at sexual reproduction, which is probably what you guys are all interested in anyway. All right, I'll see you all on Monday.